Am I audible?
Yes, sir.
Okay, so I think this is where we had left off in the previous class. I think we had discussed about this. याद आ रहा है या नहीं आ रहा है? See here, this block diagram says you have a source, and from the source, information is being transmitted to the user. Okay, so you have a controller at the transmitter end and another controller at the receiver end. So these controllers determine the receiver controller specifically determines if there is an error in what was transmitted, and this is what it will say that to the transmit controller that this particular packet has an error, a packet or block or you can say from this the data which was received after this particular block. So accordingly, the transmit controller will resend that data again. Encoder and decoder, these are necessary for error correction. So if you don't have an encoder and a decoder, mm, it's likely that your errors will be higher. So even when you have encoders and decoders, your errors are much lower. So the receiver controller would be requesting the transmit controller for repeat transmissions much lower when the encoder and decoder are present. Okay, so this is about automatic repeat request. So this is also the same about the classes that we are having. If you don't give me any feedback, I won't know whether you're receiving what I'm transmitting. So going ahead in forward error correction, there are different types of encoding and decoding techniques. So these error correction codes basically are what is mentioned here as cyclic codes. So cyclic code popular error correction coding mechanism, and this okay. So with this with these cyclic codes, uh, it's possible to have error correction. So in this forward error correction mechanism, the codes which are used are normally designated uh, as NKT. So this is a shortened form of that. So N here refers to what is the number of bits which are transmitted for a particular message, and M refers to the number of message bits. So these are part of the block codes. The cyclic codes are part of the block codes, and so you always transmit in blocks of length n. Length meaning refers to number of bits, the number of bits which you are transmitting to indicate a message block. So n contains some additional redundant bits which help in error correction. So these are some of uh, the error correction codes that are popularly used in communication systems, not just optical communications, but general communication systems. So you should keep these in mind: the Hamming code and the Reed-Solomon code. So the Hamming code is a binary code, whereas the Reed-Solomon code is a non-binary code. So both have their own advantages and disadvantages. So this is what you see. What is the effect of error correction? See, this is the x-axis indicates what is the in this figure A. X-axis indicates what is the bit error rate, and the y-axis indicates what is the BER after you introduce forward error correction. So theoretically, this is what you get, meaning the forward error correction is gives rise to lower BER compared to without forward error correction. And if you look at um, the similar figure here, the x-axis indicates what is the received power, and y-axis indicates what is the bit error rate. So for the same amount of received power, okay, if you draw a vertical line, it would indicate the same received optical power. Okay, so if you say, let's say, minus 36.5 dBm is received, then the VER when forward error correction is introduced is of the order of something of 10 to the power minus 10 to the power minus 9 something. So something into 10 to the power minus 9. Okay, and if forward error correction is not used, then you have something into 10 to the power minus 6. Okay, so you have a factor of about 10 to the power 3 between between bit error rate with forward error correction and without forward error correction. Going ahead, there are certain noise effects on system performance. So the most common noise sources are uh, the modal noise, wavelength chirp, spectral broadening induced by optical reflections back into the laser, and mode partition noise. So we'll take a look at all four of these. Now, if you look at this, modal noise is not present in single. This is not single. This is single in single mode links. Uh, but the mode partition noise, chirping, and reflection noise do play a part in even single mode links. Okay, so modal noise is what is present in multimode fibers, and this is because of uh, this can be because of mechanical disturbances along the link or fluctuations in the frequency of an optical source. So when you have a laser, it is highly likely that the laser wavelength can fluctuate because of changes in temperature of the device, or because of external factors like um, if there is some mechanical uh, vibrations uh, at the source, meaning near the laser, even that can induce fluctuations in the frequency of the laser. So, so when modal noise is introduced into digital fiber optic system, then this is how the bit error rate degrades. So as the modal noise increases, so here M here indicates the modal noise. So as the modal mm, yeah, so as the modal noise yeah, this one indicates no modal noise. So as the modal noise increases, the bit error rate increases. So if you look at the a single uh, received optical power, then as the modal noise increases, the uh, bit error rate also increases. So the other type of noise is mode partition noise, and this is something which is again because of the uh, laser source. So a laser source can support I had shown that a laser can have a wide profile, and out of that, hardly about one or two modes would be usually coupled onto a fiber. But which one or two modes would be coupled onto a fiber? That is critical here. And here you can see that at some time A, this is the uh, the x-axis is wavelength. So we have this particular mode which has highest power, and there are two other modes which have about half the power. Okay, and there are two uh, more modes which have about one-fourth the power of the main dominant mode. Okay, so if you look at the overall power output of the laser, then at some other time, it's possible that you may be getting the same output optical power, but the mode at which the power is highest, that may shift. So here the dominant mode at time A was here, whereas the dominant mode at time B is now slightly different. And beyond that, the other modes which had relatively lower power, those have also shifted. So this uh, fluctuation in intensity of different modes causes mode partition noise. For digital transmission system, for chirping, chirping is the phenomena where you have line broadening. So this is line broadening refers to wavelength broadening in case of directly modulated laser. Uh, Usually the lasers are directly modulated, and this line broadening is what is termed as a frequency chirp, and this can lead to significant dispersion effects for intensity modulated pulses. So you can see a comparison about width, length, how the bit error rate uh, is changing. So as the length of the fiber increases, the bit error rate also increases. Of course, this would depend on what is the fiber being used. So if you look at the first three in the legend, uh, you have 6 meters, 12.8 kilometers, and 19.4 kilometers. So these three are the leftmost line, and then this one, second from right, and then the rightmost one. So in these, this is as as the distance is increasing, the bit error rate is increasing. Okay, so this is hardly for 19.4 kilometers, but you can get the same amount of or even slightly better error performance if you're using dispersion shifted fibers. Okay, so if you're using a dispersion shifted fiber, then the performance that you have is given by this line, which is the second from the left. Okay, and this last one indicates with a length of 110.8 kilometers, and the fiber here is mentioned as combined. So combined here would refer to using uh, a standard fiber, and beyond a standard fiber you also need to use a dispersion compensating fiber. So when you use a dispersion compensating fiber, the dispersion can be compensated, and at the same levels of bit error rate, you can have a much larger transmission distance. And there is reflection noise. Reflection noise, when you have a system wherein you have a transmitter, an optical transmitter, and a receiver. So these two points, reflection points, so these reflections can be because of splices or couplers and filters or at any air to glass interface connectors. So these uh, discontinuities, refractive index discontinuities, these give rise to Fresnel reflection. So this Fresnel reflection would cause multiple, these can cause multiple reflections. So here at the right side you can see you have a main pulse, and this main pulse is reflected, and this is again reflected at this end, and you get it after some time as indicated by 2. So this uh, the amplitude of this reflected signal would be much lower, and if you consider that there are even more reflections, then it's possible that after a certain instant of time you'll have another reflected pulse. So when you have multiple pulses here and here and here, then these would be noise for the other main pulses which are transmitted after this. this is about what we have for the digital optical transmission. So these are examples which were already given before. Um, these examples. So the solutions of these examples are given at the end. You can take a look, and I think these are quite simple enough to understand. So here we discussed about fibers. Can you tell me, have I mentioned anything about dispersion shifted fibers and dispersion compensating fibers and polarization maintaining fibers? इनके बारे में मैंने कभी मेंशन किया है या नहीं किया, मुझे याद नहीं आ रहा है.
No, sir.
Okay, I think we can take a look at those right now. So, in optical fibers, we have material dispersion and waveguide dispersion. Material dispersion is something which is anyway unavoidable. Uh, the total dispersion that we get, that is actually a difference that you get from the material dispersion and waveguide dispersion. So based on this difference, there is a point in the dispersion line. So I think should be. Yeah. So if you look at this line, you can see the y-axis is the dispersion. Okay. So for different diameters of the optical fiber, you have different dispersion curves. Fine. So and all these curves cross the zero line. Okay, this is the x-axis uh, with the incremental value being wavelength in micrometers. So if you have a fiber with a diameter of 4 micrometers, mm, of course, this is what you have from an article which was published in 1981. So more recent or standard fibers have slightly different, but the concept here that I wanted to explain is that at a certain wavelength, maybe something around 1.55 or something, you have uh, zero dispersion, fine, when the core diameter is 4 micrometers. When the core diameter is 5 micrometers, then the zero dispersion wavelength has uh, shifted to something around 1.35 or 1.33 something. And if you look at uh, this particular curve, this is for uh, a fiber with has a core diameter of 6 micrometers, and the zero dispersion wavelength is something around, slightly less than 1.3 micrometers. Could be maybe 1.28 micrometers or something. So this is uh, this is about the zero dispersion wavelength. Okay, but when you're using the same fiber at other wavelengths, the dispersion would be present. So we have material dispersion, which is because of the uh, fiber material which is being used, and we have waveguide dispersion, which is because of the uh, um, yeah, this is because of the structure of the waveguide. Okay, and what is the refractive index of the core and cladding? Both play a part, along with what is the V number, and this V number uh, is dependent on what is the refractive index difference along with what is the core diameter. So it was uh, it was also found that the lowest attenuation, that is found at 1550 nanometers or 1.55 micrometers. So in order to have lowest dispersion also at that the zero dispersion wavelength, which is usually at 1 point or around 1.3 micrometers, that is shifted to 1.55 micrometers. So this shifted single mode fibers. So this is what you have. This is the curve that you have for a standard single mode fiber, which has a dispersion close to dispersion wavelength near the 1.3 micrometer wavelength. Whereas this is this is the dispersion curve for a dispersion shifted fiber, wherein the zero dispersion wavelength is close to the 1.55 micrometer wavelength range. And there is another type of fiber which is the dispersion flattened fiber. So if you're using a dispersion flattened fiber, then you can have very low dispersion over a range from 1.3 micrometers up to 1.6 micrometers. So it is possible to transmit higher data rates on these particular wavelengths if you're using a dispersion flattened fiber. So coming to the dispersion shifted fiber, This is the profile of a standard single mode fiber. This indicates the different dispersion because of different materials. Now, these are other different refractive index profiles which have been proposed to have the dispersion shifted fiber. So we can have a triangular profile as given in figure A, and figure B is a depressed cladding triangular profile. So anyway, the core has a triangular profile, and in the cladding, the refractive index is slightly lower, and beyond that, again, so the cladding has two parts. One part has this lower refractive index, and the other part has a slightly higher refractive index. And uh, one can also have a Gaussian profile of the core refractive index. So all these three uh, different structures can give rise to dispersion shifted fibers. So you should keep in mind that the dispersion shifted fiber is different in structure from the standard single mode fiber. So these are further advanced designs to have dispersion shifted fibers. Uh, so if you use these designs, then the dispersion is shifted to the exact wavelength, and you do not have any disadvantages as mentioned for the previous designs. So these designs are what are known as multiple index designs. Okay. So you can see here uh, the loss of these dispersion shifted fibers, however, is not the same as we get for the standard single mode fiber. So there is a trade-off here. See, this is of the same range. The normal, the standard single mode fiber that has a loss of 0.2 dB per kilometer, then this is slightly higher. So with these advanced designs, it's possible to have even better loss characteristics. And the next thing is the dispersion flattened fibers, which have the profile as shown here. So the dotted line that you see here, this corresponds to the dispersion flattened fiber. So this is not exactly flat, but it's better than the slope that you have that you can see here for the standard single mode fiber or the dispersion shifted fiber. So these are architectures of to have a dispersion flattened uh, profile or flat dispersion profile. So there are multiple architectures which are possible. So you can see here the attenuation is also low and the dispersion is flat. But with the dimensions that you see here are of the order of micrometers, so getting such refractive index profiles at such small dimensions is a difficult task. So the dispersion flattened fibers are usually not so popularly used because the cost of fabricating these becomes much higher. So this non-zero dispersion shifted fiber is another type of fiber wherein the dispersion slope is less than what you have for a standard single mode fiber. So this is how uh, or this is the profile that one can get by using a dispersion compensating fiber, meaning this is the dispersion uh, this is the dispersion that you can have. This is actually a very large negative dispersion which can be introduced by a dispersion compensating fiber. So this dispersion compensating fiber would means for every, let's say, about 100 kilometers of a standard single mode fiber, you'll be introducing some dispersion, some positive dispersion, which will be giving rise to broadening of a pulse. So after 100 kilometers of this fiber, you can introduce something around, say, 1 kilometer of a dispersion compensating fiber, and this dispersion compensating fiber, because of the very large negative dispersion, can reduce your pulse width back to the desired level. So the net uh, dispersion is almost zero near the zero line, and you can have better transmission. Yeah. So what you see here as negative dispersion fiber, this is what is also known as the dispersion compensating fiber. So you can see the complex structure of the optical fiber refractive index profile. So again, fabricating these is a very tedious task, and uh, it's very difficult to have very long lengths of this type of negative dispersion fiber or a dispersion compensating fiber. So I believe that is enough for the day. Anything you would like to ask? कुछ पूछना है? If you have no queries, you all can leave and get fresh for your next class.